Okay, we're in part 3 of section 6.6. We're now switching to logarithm equations. So we're going to use the definition of a logarithm to solve an equation. So basically, what this means is you can use the definition of a logarithm as it pertains to converting it to exponential form to solve. So let's look at this one. We want to solve for solve 2 log of 3 base 10 rather. So 2 log base 10 of 3x plus 7 plus 8 equals 12. So you want to solve for x, but before you can do that, you need to get this logarithm by itself. So we're going to subtract 8 on both sides, and we are left with 2 log base 10 of 3x plus 7, the 8's cancel, equals 4. Alright, so again, we still want the log by itself, so we're going to get rid of the 2, which we're multiplying at the moment. So to undo multiplication, we are going to divide both sides by 2. And that leaves us with log base 10 of 3x plus 7 equals 2. Okay, so now we have it in this form right here, log base b of s equals c. So what we're going to do, so this is log base 10 of 3x plus 7 equals 2. So what we're going to do is we're going to convert it to log form. So we're going to convert, we're going to not convert it to log form. It's already in log form. We're going to convert to exponential form. Okay, so remember the base here is 10. We just don't see it. So if I were to write this in exponential form, this would be 10 squared equals 3x plus 7, because remember logs equal the exponent. So the base is the same. It's 10. This is the exponent, and this is what it equals. Alright, so now you have regular numbers in an equation. So you can just say 10 squared, which is 100, equals 3x plus 7. Subtract 7 on both sides. We get 100 minus 7 is 93 equals 3x, and divide both sides by 3, and we get x equals 31. Okay, so let's look at this next one. Let's solve 6 plus ln of x equals 10. So we're going to start by getting the log part of the expression by itself. So we're going to subtract 6 on both sides, and we get ln of x is equal to 4, because 10 minus 6 is 4. And now that we have it in this form, we can rewrite it in exponential form. Now what is the base? The base here is e, and the exponent is 4, and that means it equals x. So all we have to do here is e to the 4th. So let me just make sure you know how to do the e. I think we discussed it in a previous video, but just in case. So if you have the TI, you would hit second ln, e pops up to the 4th power, 54.5982. 5982. But let's also do it on Desmos, just in case. So for this, you can actually just type the letter E. Alright, carry to the 4th power, and 54.5982. So same answer, either type of calculator. Alright, so let's do another one. 3 natural log of 2x equals 9. So you want to get the natural log of 2x by itself. So we're going to divide both sides by 3, and we'll get the natural log of 2x is equal to 3. Now that we have it in this format, we can convert it to exponential form. So the base is e, the exponent is 3, and that leaves 2x to be on the right side. Now, in this case, we're not quite finished yet, because we want to get this x by itself. So we're going to divide both sides by 2. So x equals e to the third divided by 2. So I'm just going to do second ln to the third divided by 2. I get 10.0428. 0428. 10.0428. Okay. Here we go. Alright, so let's try another one. We want to get this by itself first, so we need to get rid of that 2, so divide both sides by 2, and we end up with ln of x plus 1 equals 5. Now that the ln is by itself, that x plus 1 is stuck together, okay? That's what you're taking the natural log of. We're going to rewrite this in exponential form, so this e to the fifth equals x plus 1, and we want to get x by itself, so we're going to subtract 1 on both sides, and we end up with e to the fifth minus 1 equals x. So we can just go here, e to the 5 minus 1 equals x, and that's 147.4132. Let me just double check, make sure I wrote that right. 147.4132. I didn't. I flipped some numbers. It's 4132. Alright, let's just see how we would do this in Desmos. In Desmos, we would do e to the fifth minus 1, and we get the same thing. Alright, let's see. We can also solve log equations by using a one-to-one property, similar to what we did with the exponential equation, solving them by the one-to-one property there. Basically, what it says is if you've got log base b of s and log base b of t and they're equal, so basically what you're noticing that the bases, oops, I want to use this instead. The bases are the same. If the bases are the same, then that means that s and the t must equal. Okay, so you can use that fact to solve logarithms. So the first thing you're going to do to use this method is you're going to use the rules for logarithms to combine like terms if necessary, so that the resulting equation is in this form. Log base b of s equals log base b of t. Basically, log with the same base on each side of the equation. Then we're going to use the one-to-one property to set the arguments equal, and then we're going to solve the resulting equation for the unknown. So let's look at this one. So here they have the same base. These two sides of the equation. It's base e, right? So that means that this and this must equal. So 50 minus 4x must equal negative 5x. And then you just solve it. And then you just decide, how you want to rearrange this to solve it. I'm going to add 4x to both sides. And I get 50 equals negative x, which means x equals negative 50. Alright, so let's look at this one. So again, this is same base. The base is e again. So we can use that one-to-one property. So we know that x squared must equal 1. So if you're going to solve both sides, we would square root each side. So you would end up with x equals plus and minus 1, and then I would just plug both in and just double check. Either way you end up with the same answer. So 2 answers here, 1 and negative 1. Alright, let's look at this one. So this one, it's not in the correct form yet because you've got 1 log on the left and 2 logs on the right. So you want to use your properties of logarithms to simplify that. So I've got log of x plus 12 on the left. I can't really do anything with that. But on the right, I have log of x plus log of 12, base 10 here. So I could rewrite this as, using the product rule, this would be log base 10 of 12x. So now they are both log. This is a common base. This is a base 10. So now I can say that x plus 12 equals 12x, and you're going to solve it. So x plus 12 equals 12x. So subtract x on both sides, and you get 12 equals 11x. Divide both sides by 11. X equals 12/11. Then you're done. All right, let's look at this one. Natural log of x plus 6 minus natural log of x equals natural log of 58. So we can see we have a common base of e, but we need to combine the ln's on the left so that we can write it as one log. So we're going to use the quotient rule. X plus 6 over x equals ln of 58. So that means that x plus 6 over x must equal 58. And then we're going to solve. So because I've got x in my denominator, I need to get rid of that. I need to get it out of the denominator. So I'm going to multiply both sides by x. And I end up with these x's cancel, and that leaves x plus 6 equals 58x. And then I'm going to subtract, no, I don't want to subtract 6. I want to subtract x from both sides. And I get 6 equals 57x. So then I'll divide both sides by 57. So x equals 6 over 57. Okay, so that brings us to applying this to real world problems. Now, I wrote at the top here a formula that I think I introduced in an earlier video that you will use for a lot of the homework. But they start off with an example that uses the following formula right here. A of t equals a sub 0 times 1/2 to the 1 over t. But just note that the vast majority of the word problems in the homework, you can use this where the a sub 0 is the initial value. The a of t is the value over time. K is usually some sort of rate. T is usually time. And so you can use that to set up the equation, and then you can solve it. Okay, so looking at this one, we have a of t equals a sub 0 times 1/2 to the t over t. So that looks like a 1, but that's a lowercase t over uppercase t. A of 0 is the amount initially present. T is the half-life of the substance. T, lowercase t, is the time period over which the substance is studied, and y is the amount of substance present after time. So in this case, I think what they mean by y is the a of t. So let's go down here, and they say, the word problem is a little hard to read, and I apologize for that. It says, how long will it take before 20% of our 1,000 gram sample of uranium-235 has decayed? So a sub 0, I can go ahead and tell you, is 1,000 grams. Okay, so your a sub t, or your y, that is the 20% that it decays. So if it decays 20%, what's left over? What's left over is 80%. 80%. So what is 80% of 1,000? And that would be 800. So A of t is actually 800. And let's see, what else did we need? We needed lowercase t and uppercase t. So uppercase t is the half-life, and the half-life is for uranium-235. So we get that from this table here. And look at this, you guys. That is the half-life. 703,800,000 is the half-life. So 703,800,000 years is the half-life. And let's go back to the equation, the formula. A of t is equal to A sub 0 times, I believe it was 1/2. Yep. To the t over t. So lowercase t over uppercase t. So let's fill in what we know. We know that 800 is our A of t because it's decayed 20% to 80%. 80% is what's left. A of sub 0 is 1,000. 1/2 stays 1/2. We don't know t. And uppercase t is, yikes, 703,800,000. Okay, so we want to solve this. You might think, how in the world? But we're going to use those techniques that we learned previously. So this is an exponential function. So what we can do is we can divide both sides by your 1,000 so that we can get the exponent, the base and the exponent by itself. So 800 over 1,000 is 0.8 equals 1/2 to the t over 703,800,000. And so if you will recall, when we have exponential form and we're kind of stuck here, remember what they told us to do. They told us to take the natural log of both sides. So we're going to, and let me just write this in different colors so you can see. So we're going to take the natural log of 0.8, and then we're going to take the natural log of 1/2 t over 703,800,000. Okay. So then what happens is this one, it gets a little complicated. Alright, so what you can do is you can take that exponent, and remember now that it's a log, we can take it and we can move it to the front here. And I'm going to, yeah, okay, I do have an extra paper. Okay, so I'm going to actually scroll down a little. Let me rewrite what I have here. I have natural log of 0.8 is equal to, and we're moving this t over 703,800,000 to the front. So t over 703,800,000 using the power property of exponents times ln of 1/2. Okay, so our goals is to get this t by itself. And all I've done so far is I took the natural log of both sides, and then now I'm moving the exponent in front of the natural log using that power rule for logs. So I want the t by itself. So let's get rid of the ln of 1/2. So I'm going to get rid of that by dividing it on both sides. So you can do ln 1/2 or you can do ln 0.5. And it cancels on this side and just leaves t over 703,800,000. On the right, I have ln of 0.8 divided by ln of, I'm just going to write 0.5. And I want t by itself, so now I am going to multiply by 703,800,000 on both sides. Okay. So, I mean, the biggest thing here is just writing that big long number there. So the 703800000s cancel on the right and leave t. On the left, I have 703,800,000 times the natural log of 0.8 over the natural log of 0.5. So let's do that in the calculator. So 703,800,000 times the natural log of 0.8 divided by the natural log of 0.5. And we get 226, it's down, 226, 572, 993.2, and then if I remember correctly, it said, how long will it take before 20% of it is decayed? So I'm just going to write the 0.2. It doesn't say to round years. Okay, so that's a really large answer, but that is the correct answer. So as you're going through the application problems, just remember this formula here can be applied to so many of them. A of 0 is the initial value. Not all of them are going to look exactly like this one right here. But for most of them, you can use this formula, and then you will solve. If you run into any trouble, definitely let me know. I will be happy to help you through those. Another formula that you might be able to use for some of them is just your basic exponential formula, y equals a times b to the t, where a is the initial value, and then b is your growth factor or your decay factor. Okay, so if you have questions, let me know.